For more physics-related videos, please subscribe. Welcome to Stellar Physics 6C. In this video, I'm going to cover core collapse supernovae. In general, this is a very complicated topic that is not fully understood. So in this video, I'm going to overview qualitatively what we know and what we don't know about core collapse supernovae. I've rated the physics level in this video as intermediate. Let's start off by briefly recapping where we're at in the stellar life cycle. Initially, we have a collapsing dust cloud that forms into a main sequence star. This is the hydrogen burning phase. When hydrogen in the core runs out in this star, it will move on to the next phase, which is helium burning. This is the red giant phase. After helium burning, the next stage is carbon burning, and if the star is sufficiently massive, it will fuse all the way up to iron. At that point, you cannot fuse any further, and that's when you get a core collapse supernova leaving behind either a black hole or neutron star remnant. The material ejected in the supernova may eventually find its way back into a collapsing dust cloud, and the whole cycle starts again. In order to fuse all the way up to iron, the star has to have a mass of about 10 solar masses or greater. So now let's jump to moments before core collapse. The star has fused all the way up to iron, so it looks like this sort of onion with various layers of different nuclei, with the heaviest generally closer to the center, and the core being predominantly made up of iron and nickel. At this point, we cannot fuse any further, or more accurately, I should say, further fusion no longer releases energy, which is how the star was being supported against gravity in the first place. So now, there is nothing to support the star against gravitational collapse, and so the star will now collapse. The reason further fusion does not release energy is because iron and nuclei around iron have the highest binding energy per nucleon. So as you move from hydrogen down to iron, you're releasing energy. The nuclei have lower and lower energy. That energy is being released, and that's what's supporting the star against gravitational collapse. Once you get to iron 56, further fusion requires energy to be put into the nuclei, and so instead of releasing energy to support the star against gravity, you're actually sucking energy out of the star. But just to be clear, even though it is commonly said that you cannot fuse beyond iron in stars, actually you can fuse beyond iron, as somebody in the comments on a previous video pointed out, correctly I should say, but we're going to find out that once the supernova goes off, all these nuclei that are created beyond iron aren't going to survive because the supernova is initially going to disassociate all of the nuclei. So all of the nuclei and elements beyond iron that we see in the world do not come from the fusion that's taking place at this point. Now that the stage is set for core collapse, how does it actually work? So at this stage, we have an iron-nickel core, and as I just explained, at this point the star has lost all of its support against gravity because fusion will no longer release any energy. So the star is now going to collapse under gravity. In the process, this will rapidly increase the temperature and the density, increasing the rate of nucleosynthesis beyond iron as the material in the star moves towards nuclear statistical equilibrium. What is nuclear statistical equilibrium? This is when the nuclei reach an equilibrium point where the capture rates, or the fusion rates, are equal to the dissociation rates. So in simple terms, every nuclei is being created at the same rate that it's being broken up. So on net, there is no change in the nuclear composition of the material. As I said, this is just the core. Remember that the core is surrounded by the outer layers of the star, and they're also collapsing. Now, one very important thing we have to remember here is that because the temperature is so high at this point, the neutrino luminosity is extremely high. The neutrino emissivity, which is the luminosity per unit volume, scales as the temperature to the 9th power. So as the temperature increases, the neutrino luminosity increases enormously. And this sucks out energy and, more importantly, entropy from the star, essentially freezing the star. If you want to understand more about this process, I covered it in detail in Stellar Physics 4G, where I explained why stars are giant freezers. But essentially, this is it. The neutrinos suck out all the energy and entropy from the star. So now we have this collapsing core that it's simultaneously freezing or losing all of its energy and entropy, until eventually inside the core you get what's sometimes called a proto-neutron star. This is essentially a highly degenerate core of nucleons, mostly neutrons but some protons as well, with a very high temperature of order 10 billion Kelvin. But despite this high temperature, this core is basically frozen because that's what degenerate matter is. It's essentially the coldest material you can get. So if we picture two different energy wells, and the further up the well the material is, the higher energy it has. So in this case, on the left, we have the energy distribution of normal matter, matter we're used to every day, a Maxwell-Boltzmann gas, which obeys things like the ideal gas law and everything you learn in introductory chemistry courses. What's important about this type of matter is that the matter is mostly distributed above what's called the Fermi energy. So all of these lower energy states are unoccupied. For degenerate matter, the material is distributed with the lowest energy possible. So all of these lower energy states are occupied, and a small percentage of the material will have energy above the Fermi energy. If the temperature were exactly zero, then the highest energy occupied would be the Fermi energy. That's how the Fermi energy is defined. In this case, our temperature is not zero, it's 10 billion Kelvin, which you might think is really high, but it's actually not high compared to the Fermi energy. So despite having this enormously high temperature, the core is basically as cold as it can possibly be. In fact, it's basically the coldest thing in the universe. So now you can see why we're saying that stars are giant freezers. Another way that it's sometimes put is that as stars heat up, they cool down because their temperature goes up to 10 billion Kelvin, but they freeze and thermodynamically become as cold as they can possibly be. If you want a better understanding of degenerate matter, I covered it in detail in Stellar Physics 4C. Now, in the case of core collapse, why is this relevant? Well, you have to think about what degenerate matter really is. Quantum mechanics, and specifically the Heisenberg uncertainty principle, says that you cannot confine a particle to too small of a volume. There has to be some wiggle room in its position. Well, for highly degenerate matter, the material is so dense that you've pushed it to this limit where quantum mechanics says you cannot confine the material to a smaller volume. And this results in an extraordinary pressure within the material, which is called degeneracy pressure. So what has just happened? The star is collapsing because it's lost its pressure support. But now we form this degenerate core which has enormous pressure, and it's going to act as a wall onto which this infalling material is going to slam into, causing a shock wave that's going to move outwards. And in the process, it's going to blow out the outer layers of the star and crunch down the core, which may either crunch down into a neutron star or a black hole, depending on the mass of the star. We'll get into what's left over after the supernova at the end of the video. For now, this shock wave that blows up the star, or the outer regions of the star, is the supernova. And this spectacular explosion will result in our process nucleosynthesis, meaning it's going to make nuclei beyond iron. If you're finding this video interesting so far, please be sure to like and subscribe if you haven't already, and maybe share it with a few friends. Alright, so that's the basic plot of a core collapse supernova. But the devil is in the details, and this is where things get a little bit dicey. We don't really understand how the supernova goes off exactly. So let's take a look at the core collapse supernova in greater detail. We have this degenerate core that acts as a wall. The infalling material slams into this wall. It then bounces back outwards, but the outer layers are still falling in, and so the two are going to collide, causing this shock wave which propels outwards and blows up the star. And this theory was essentially developed by a man named Hans Bethe, who is basically the father of nuclear physics. He basically invented nuclear physics. And he came up with this theory for core collapse supernova and how nuclei beyond iron were made in the universe. Well, that was a very attractive theory, but then when you started calculating exactly what was going to happen, as well as running simulations, it was found that all the energy in the shock wave did not blow up the star. Instead, it went into breaking up all of the nuclei that had formed throughout the stellar life cycle. And so all that energy now was not available to blow up the star, and this killed the supernova. It was said at the time that Hans Bethe, despite having invented nuclear physics, when coming up with his theory of core collapse supernova, had forgotten about nuclear physics. So this was a problem. Now you have to remember, at the time, simulations were very primitive. So these crude simulations could not get the supernova to go off. But then something interesting happened. A scientist running simulations for supernovae was working in a team, and at that time, at the facilities he was working at, each team had something like 20 hours of computation time they were allowed to use for the entire year. And so it was very important that when you ran a simulation, you had a kill switch, so that if something went wrong with your simulation or if it was taking too long, it would shut off to make sure you didn't use up everyone's computation time. Well, as the story goes, this researcher ran a supernova simulation one night and messed up the kill switch. And the simulation ran all night and used up the entire year's worth of computation power for his team in one night. And the next day, when the team found out, this was essentially a disaster. However, when they looked at the results of the simulation, they found that the supernova in fact exploded and created all the R process material. So essentially the problem was their simulations weren't running long enough, because while it was true that a large part of the energy of the supernova was going into breaking up all of the nuclei then fused back together, releasing energy again, and if you waited long enough, the star in fact did explode, and it made all of the heavy elements beyond iron in the universe. So this botched simulation turned out to be a huge success. You got your supernova, and you made all of the R process material in the universe. All is good, we've explained everything. Well, not so fast. At that time, neutrinos were not included in supernovae calculations. When people started including them, they found that neutrinos carried away 99% of all of the energy in the supernova, which works out to about 10% of the rest mass of the star. So this immediately killed the supernova because while you had enough energy to blow it up, all of it went into neutrinos, which basically just left the star. So there was nothing left over to blow up the star. Furthermore, even if you somehow did manage to get the energy to blow up the star, the enormous number of neutrinos killed the R process via what's called the alpha effect, which I covered in Stellar Physics 5H. But let me briefly recap how it works. In order to make R process material, the R stands for rapid neutron capture, you need a lot of neutrons around with a small number of seed nuclei for them to pile onto. This means you need to have a low YE, where YE is called the electron fraction, but it's also the same thing as the proton fraction, so it's the number of protons per nucleons. You don't want a lot of protons per nucleons, you want a lot of neutrons per nucleon, because you need a lot of them around to pile on and make R process material. So what happens when you introduce neutrinos? Well, when you have neutrinos, you can get this reaction, where you have a neutron plus an electron neutrino. There are three types of neutrinos: electron, muon, and tau. Specifically with electron neutrinos, they can capture with neutrons to make a proton plus an electron. So what does this mean for the R process? We have this seed nucleus with a bunch of neutrons around it. An electron neutrino comes along. It captures on the neutron, converting it to a proton. It also emits an electron, but we don't care about that right now. That proton will then capture with another neutron, creating a deuteron, which is an H2 nucleus, hydrogen 2. And nearby, the same process will take place with another neutron and electron neutrino, and then those two deuterons come together and make an alpha particle, a helium nucleus. Now, alpha particles are very stable. Once you make an alpha particle, that's it. It's stuck as an alpha. So what has just happened? The presence of neutrinos, and specifically electron neutrinos, takes 4 neutrons and converts them into an alpha. And so now all of your neutrons that were available for the R process have been locked up in alpha particles, and this kills the R process. So what happens now when you introduce neutrinos? If we take a look at a plot of the relative abundances of nuclei in the universe, for the R process, we're looking at stuff beyond the iron peak, so everything over here on the right side of this plot. Now we can see here that we have 3 peaks, and they're double peaks. So one has an R, one has an S. The R is for R process peak, and the S is S process peak. We don't care about the S process peak, that's another mechanism. But when you include neutrinos, the alpha effect ends up stunting this R process somewhere around the second peak, depending on exactly how you run your simulation. It's very difficult to get to the third peak if you have neutrinos present. So this was a problem. Most introductory textbooks will tell you that heavy elements beyond iron are all made in supernovae. But actually, this doesn't work because of neutrinos. So this is another unsolved problem in supernovae. So going back to the physics of core collapse supernovae, we have these two problems. The neutrinos carry out all the energy, so we can't blow up the star. And even if we could blow up the star, the neutrinos kill the R process, so where do heavy elements in the universe come from? So this is still an unresolved problem. Regarding the energy problem, the most commonly proposed solution is called neutrino reheating. So here the idea is that a small percent of the neutrinos will interact with the material and transfer their energy to the star, and that will cause the star to blow up. So about 1% of the energy carried by the neutrinos gets dumped back into the star, and despite being only 1%, this would be enough to blow up the star. But you have to remember that neutrinos basically don't interact with anything. They only interact through the weak nuclear force, which, as its name suggests, is weak, so the probability of them interacting with stuff is very low. Now, we only need 1% of the neutrinos to interact, but that's still very difficult to do. So how this neutrino reheating takes place, if that is in fact the solution to this problem, is still not understood. But generally speaking, this is what is thought to happen. Somehow, a small fraction of the energy in the neutrinos gets dumped back into the star, and that is enough to blow it up. Now, how about the R process? Now, what's proposed here is that somehow the neutrinos, remember there are three types of neutrinos, and it's only the electron neutrino that's relevant to the alpha effect. So what's proposed is that somehow the electron neutrinos change into the other types of neutrinos. The three types of neutrinos are called flavors. Okay, so the idea is the electron neutrinos change their flavor to either a mu or a tau, and the mu and tau neutrinos aren't relevant for the alpha effect. Now, we don't actually know if this is what happens. We know this is possible. In fact, this was observed with the sun. The sun emits a lot of neutrinos, and when we were trying to detect them, we couldn't do it. This was called the solar neutrino problem. And then it was found that because the neutrinos are traveling through material, even though they're not interacting with it, the matter around the neutrino has an effect that causes the neutrinos to change their flavor. And the reason we weren't detecting them is because we were looking for the wrong type, the wrong flavor. Once we started looking for the correct flavor, accounting for this change in neutrino flavor taking place within the sun, we were able to detect the neutrinos leaving the sun. So essentially, the same mechanism is proposed to take place within the supernova somehow, eliminating all or enough of the electron neutrinos that you get the full R process all the way up to the third peak. Again, how this would exactly take place is not understood, if it takes place at all. There is always the possibility that supernovae are not the source of most of the R process material in the universe. The other big candidate is neutron star merges. So this would be two neutron stars colliding, and in the process, they eject a bunch of material, and that would be the main source of elements beyond iron in the universe. That theory also has its set of problems, and I'll cover it in the next video when I go over neutron stars. I also actually covered it in Stellar Physics 5H. Okay, so that is basically the current state of physics regarding core collapse supernovae. We don't fully understand how they take place, but we know they do take place because we've observed them. And you can see that historically we kept thinking we understood core collapse supernovae, only to find out there was a new problem we hadn't thought of. My thesis advisor used to say, we've always understood how core collapse supernovae work, it just changes every year. Regardless of the details of how supernovae are set off, they are set off because we observe them, and they are extremely powerful explosions. They are as bright as about 10 billion suns, and they release about as much energy as all of the energy released by the sun over its entire lifetime, which is 10 billion years. Only in the case of the supernova, that energy is released in about a month. So this is a truly spectacular explosion. Remember that 99% of that energy is still released in neutrinos. So even though we can observe these spectacular explosions by the light they emit, that still only corresponds to 1% of the energy being released. In the previous video, Stellar Physics 6b, I went over Type 1a supernovae, which is exploding white dwarfs. And in that video, I explained that they all look exactly the same. So if you see one go off, you immediately know what it was. In the case of core collapse supernovae, they're not all the same. There are different types, and their light curves are different for each type. So here we have the luminosity, or the brightness, in units of absolute magnitude. If you don't know what that is, it doesn't really matter. It's just a measure of brightness. All you need to know is that this is a log scale. On the horizontal axis, we have days since the peak luminosity. So all of these different lines are different types of supernovae. This black line, which is the brightest of all, is the type 1a supernovae. So this is the only one that's not from core collapse. And these different types of core collapse supernovae have different light curves and are generally categorized based on whether they have hydrogen or not. So now that the supernova has gone off, what is left over? Well, there are two options. The core that, remember, caused this wall for the infalling material to bounce off of, which caused the supernova, crunches down and will either create a black hole or a neutron star, depending on the mass of the star. Here we have a plot of the initial mass in units of solar masses versus the metallicity, which basically just means the composition of the star, and the different outcomes at the end of the star's life. So we can see we have various types of supernovae here, corresponding to either a neutron star or a black hole. So generally speaking, for lower mass core collapse supernovae, you get a neutron star, and above 20 or 25 solar masses, you get a black hole. White dwarfs are below 10 solar masses, so this is where, if the white dwarf were to explode, you get a type 1a supernova. And notice that there's an entire region between about 40 and 100 solar masses where you don't even get a supernova. The core just collapses directly to a black hole. This is because the infalling gravitational energy is too strong to be overcome by the explosion. And before that, you get a weak supernova, which falls back into a black hole. Now, between about 100 and 260 solar masses, you get what's called an electron-positron pair supernova. This is an entirely different type of supernova, which I covered in detail in Stellar Physics 4F. By the way, these graphs are the results of simulations. So that's a basic rundown of how core collapse supernovae work. As I said at the beginning of this video, the details are very complicated, and to understand it in greater detail, you need a very advanced level of physics. And even then, we don't really understand how they work. This is still an unsolved problem in astrophysics. In the next video, I'm going to cover neutron stars, which are one of the remnants of core collapse supernovae. So if you enjoyed this video and would like to know more, be sure to like and subscribe and hit the bell to be notified for the release of future videos. Thanks for watching, and I'll see you in the next one.